Okay, so we are back working our way through chapter 2. We've been in chapter 2 for quite a bit now. Learned a couple of important things. One of the most important things that we're kind of getting into is how to name our ionic compounds, and along the way we learned about what anions are, what cations are. We learned how to predict the charges. We learned how to predict formulas based off of the different elements that are reacting, right? So one of the ways that we have of predicting formulas is looking at what we think the charge is going to be and then making sure that everything kind of balances out, right? The name of the game is the light and the dark have to be balanced, the good, the bad, the positive, the negative, right? As with everything in life. So predicting our names and predicting our charges and predicting formulas, and all that's going to kind of lead into how we can start to name ionic compounds, right? We learned about the distinction between variant and invariant, right? Invariant is most of the periodic table. Variant is our transition metals, right? The stuff that's in the middle, right? And we learned the different naming rules of how to deal with variant versus invariant, okay? A lot of information kind of densely packed into this chapter here is what it is. So I think today the rest of what we're going to do is kind of go through some naming, things like that. And then there's going to be quite a few practice problems of that sort. And then we'll see, we might get into chapter 3, if not today, then for sure by Friday, okay? I'll open another quiz for you guys on Friday there, so just keep an eye out for that. It's going to be a little bit of practice with naming and that kind of thing, and looking at your element charges and that kind of fun stuff. Okay, sound good? So it'll be like last time. It'll be online, and you guys will have, you know, a day or plus to kind of get it done. Okay? Yeah. What's up?
You might have already said this, but do you know when the other quiz will be graded?
As soon as I get to it. Yeah, I haven't quite gotten to it yet. I've got a laundry list of things that I'm kind of working through, but I'll get it done for you guys soon. Okay, sound good? One more thing in the recap. The very, very, very important thing of your polyatomic ions. Don't forget, that should be something you guys should be working through now, right? Looking at them every day, memorizing them, know the name, know the charges, know the formulas, all that kind of stuff that goes with it. All right? Cool. Okay, I think that's all we need on the recap side of things. So let's start with prayer, and then we'll continue on kind of examining this stuff here. But Lord, we just thank you for another chance. Lord, we thank you that we can turn to you whenever we want, whenever our hearts seek to just talk with you and spend time with you, Lord. And we just pray that you give that fire in our hearts more often, Lord. We want to spend more time with you. But we just pray for a time of reflection with you each day. Lord, give us the opportunity to spend time with you, and just help us to enjoy it, help us to grow out of it, help us to know a little bit more about you, who you are, and how much you love us, Lord. We just pray that we can grow to understand you and grow in our relationship with you as we grow with our relationship with our friends and our family around us. Just help us to reflect you to those around us, Lord, and give us a chance just to speak with them, to share with them, and to point them towards you also. And we just ask all this in your name. Amen. All right. So, important slide. Okay, we have two types of ions that we're going to be dealing with. We have the monoatomic ions, and then we have our polyatomic ions. The polyatomic ions are the things that you guys are going to memorize. That's that list, that's that table, okay? And the monoatomic are what we learn how to name, okay? The key distinction and what's going to be important is understanding what the endings are for your different ions. IDE indicates you have a monoatomic, fluoride, chloride, bromide, oxide, nitride, yada yada-ide, yep, okay? And then the ITEs and the ATEs are for your polyatomics. Your sulfates, your sulfites, your nitrates, your nitrites, your phosphates, yada yada yada, okay? So paying attention to the ending is going to give you information about what species you have available, or excuse me, what species of ion you have there. Good? So I told you that the polyatomic ion list is a little bit intimidating. What we're going to do is kind of take a look at kind of how it's broken down, okay? Okay, there it is. Next slide, ready? No, okay, of course not. So we have the two endings. We have the eights and we have the ites. the most part, the majority of the ions you're going to be dealing with are going to end with either ate or ite. As it says there in the little bubbles, the ATE ending just indicates that there are more oxygens. The ITE has less oxygens than the ATEs. I am not saying that every time you see an ATE, it means you have 4 oxygens. That's not what I'm saying. I'm saying the eights have more than the ites. Sometimes it's 4 oxygens, sometimes it's 3. We're going to learn later on in the semester how and why that happens. But for the moment, we just kind of have to put it in our back pocket and memorize it. You ate more at the buffet, all right? You ate more oxygens. You get big and fat and happy, right? That's kind of what I think about when I remember my endings. Eights has more. Okay? We have a couple of, let's say, opportunities to learn some complex ions that we see over and over. I should be careful. The complex ions actually mean something. We have opportunities to, let's say, look at some of these common polyatomics with hydrogen. So sulfate, right here, okay? Remember, we have to balance charges. Hydrogen has the opportunity to either gain 1 electron or lose 1 electron. The majority of the time, it's going to lose 1 electron, so we tend to see it as a +1, okay? Hydrogen's a little bit weird, but there you go. In fact, it's going to be a +1 a lot, and that +1 is extremely important. When we get into the second semester of general chemistry, we're going to talk about acid-base reactions a lot, and so that's all based off of how hydrogen is reacting, okay? But my point being this, sulfate starts with a 2- charge, right? If I add a hydrogen to it, right, I still have a 1- charge there, okay? We'll talk about how that can exist, that kind of thing. We're getting there, don't worry, okay? But if I have 1 hydrogen here, right, we drop down to a 1- charge instead of a 2-, and we just call that the hydrogen sulfate ion. The common name is bisulfate. You guys don't need to know the common names. I need you guys to know the systematic names. So hydrogen sulfate, right? Carbonate is one of our polyatomics. CO3 with a 2- charge. If I have 1 hydrogen that's associated with it, we call that just hydrogen carbonate, okay? So pretty easy. If you have a hydrogen with it, just put hydrogen in front of it. Everything else is the same. Sound good? Sometimes chemistry is not that bad, right? We just add hydrogen when we have a hydrogen. Okay. So we can't make things too easy though. Predominantly, we tend to see 2 forms of ions, sulfate and sulfite, okay? Nitrate and nitrite, phosphate and phosphite. So most of the time we just see the eights and the ites. There's an exception to this. The exception is when you have your halogens as your polyatomic ions. What are halogens? Where are they on the periodic table? They're on the right-hand side. They're group 7A or 17, right? Fluorine, chlorine, bromine, iodine, right? FClBrI. Good? Now last time I gave you guys one of the most important bits of information when it comes to reading the periodic table. Why do we call the halogens a family? Or a group? Yeah.
We have
they have similar properties, right? So would it make sense that if they have similar properties, they have similar reactivity? Sure. If they have similar property and they have similar reactivity, would it make sense that they would react in a similar way if we give it a lot of oxygen to react with? Sure. Would it make sense then that they would form similar ions? Sure. Would we expect the names of those to be similar? Sure. Everybody follow along with that step 1, step 2, step 3, step 4 there? If they're in the same family, we expect similar reactivity, we expect similar ions to form, we expect similar names. That's all I'm saying. Okay? If you guys are stuck on an exam or a quiz on the MCATs, or you're stuck on the side of the road, right? Just remember that, okay? Stuff in the same family won't react the same way. It's not going to help you change the tire on the side of the road, but at least distract you in case you're nervous. You got what I mean? Right? Maybe not. All right. So watch. What do we do? So with your halogens, we have 4 options for our ions. Starting up the top, right? Just looking at the back end here. 8, 8, I. So that holds true. The 8s have more oxygens than the ites. Good? Nothing different about that. How does this change? 4, 3, 2, 1. Okay? You can all count that. I think that's useful. What else changes as we're going through these different ions? The oxygens change from 4 to 3 to 2 to 1, right? We have the different halogens in there that could be different. What doesn't change? The charge. Got it? All of these are going to be -1. Whether it's per chlorate, chlorite, hypochlorite. Charge is always going to be -1. So what's the only thing that changes? The amount of oxygens. That's it. Got it? So how do we name this? So here's our fluorate, fluorite. We add the per prefix there just to indicate the most, okay? I don't know what per actually means in terms of grammatical. Maybe you guys learned that in one of your classes. I don't know, right? At the bottom, we have hypo, though, right? So hypo, we have the least amount of oxygens there. Okay? That's it. You guys with me on this? So the question down there at the bottom is kind of what I'm getting you to think about. How are all these things related? They're in the same family. So question. Ooh, a little bit too ambitious there, right? How would we name that ion? That is not on any table that you guys have. Oh no, he's making things up that we've never seen before. Horrible, horrible, horrible. Where is iodine on the periodic table? It's in one of the halogens. So it's going to fall under this naming system. Got it? It has 3 oxygens, so its ending is going to be 8. We take the stem, iodate. Got it? That's all it is. What is IO3, 1 minus? It's the iodate ion. Okay? Everybody with me on that? Not too bad, right? Okay, how would we name BRO with a 1 minus? Yeah. Hypogromite. Got it? Do you see what I'm doing here? It's either fluoro, chloro, bromo, or iodo. And you just plug it into the blanks there. That's all it is. All what you have to recognize is the number of oxygens and remember what the prefixes and suffixes are. Good? Cool. All right, so I've talked for a whole 15 minutes already. That's way too much work for one day. All right, give me some names. I'll give you guys a little bit of help along the way here. Okay. Up at the top, these are all invariant ions, invariant metals. Just be careful. Find the names, follow the rules, see what you can come up with. For the second one. For the second one. Just be careful. It's not CL, it's just CL. Yes. No, it is. It's right here. Okay. No, it's okay.
So it's carbonate.
Mhm. So that'd be capital C lowercase though. So if it's every second letter would be lowercase. So it would be C lowercase though. Sometimes it would be C oxide. How's that? No. These are, it'd be a lowercase letter if it was, yeah. Sometimes a little bit hard to see, especially from the back, right? Not gonna trick you guys like that. So remember, when you name the first one, you don't change that end of two. You don't change the end of two. Just like here, it's so deep. Working through it. So where's your, what I want you guys to start to look at is how can you develop skills to name things, right? So remember the first one was organic versus inorganic. Well, it's always going to be inorganic in this one. Is it covalent versus ionic, right? Is it ionic? Is it go back and you notice how you name the cation part, the metal, and the anion part, the non-metal part, right? And then you just put those two names together, right? So just like for this one here, right? The metal part is sodium, which we just keep that the same, right? We just, that's the name of it. Then you take, but be careful with that sodium. This is just chloride, right? This is a monoatomic, right? So we take the stem, All right. So I know you guys might not be done yet, but let's talk something through for a minute. How do we go through and name these? Well, remember, we have to figure out what in the world we want to name first. We have the different branches of naming. Inorganic versus organic naming. Are we ever going to do organic naming in here? No. Okay, so that's kind of a gimme question. We're doing inorganic naming, right? We have covalent versus ionic. Important question to ask yourself. Are these covalent or ionic, and how do you know? Covalent is covalent is non-metal and non-metal. Ionic is metal and non-metal. Good? These are ionic. They all have a metal and they have a non-metal. Once we know they're ionic, then we ask, are they variant or invariant? And each way is a separate way of naming it. With me on this? Let me back up here for just a second in my notes. How do we name the positive part of it? We just give the name of the metal, right? If it's invariant, just the name of the metal. If it's variant, we have to give the name of the metal plus the charge, okay? How do we name the negative side of it? If it's monoatomic, the stem plus the IDE, or the polyatomic. These are the two slides to get to your names for your ionic compounds. Got it? So if we scroll back down, blah, 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 right? We start with the top one here that everybody is probably familiar with, hopefully, right? Which part is the metal? Sodium or chlorine? Sodium. Okay. Is it variant or invariant? Invariant. So how do we name the metal, the cation part of an ionic compound? If it's invariant, all we write is sodium. Got it? Do we change anything to it? Nice and easy, right? Life is good. Life is fun. Okay, so we took care of the sodium part. Now we got the chlorine. Is chlorine monoatomic or polyatomic? Monoatomic, how do you know? Do you have to memorize that? Sort of, right? There's only one atom, got it? If there's only one atom, it has to be monoatomic. Otherwise, English isn't a thing and we have to pick a different word, right? You guys with me on this? There's only one atom, monoatomic. How do we name monoatomic? Stem plus IDE, okay? So sodium, chlor, I, got it? Stem of the element plus the IDE ending. Fair? So hop down to this one here. SRO, what do we got? What's SR? Strontium, is it a metal or a non-metal? Metal, okay. Is it variant or invariant? Invariant. Strontium, okay. It's bound with an O. O is our non-metal. It's monoatomic. You take the stem plus IDE, so strontium, ox, I. Got it? Everybody with me on this? That's all it is. Stem plus IDE ending for your monoatomics. Okay? So if we take a look at number 2 there, we go through the same set of rules. Magnesium's our metal. What is CO3? That's carbon 8. That is one of our polyatomics. Got it? How do we name our polyatomics? How do you guys name them? Through memorizing them. Got it? How do we name a compound with them? If it's called carbonate because you memorized it, guess what? It's in the name. Carbonate. Good. So what do we call this one? Magnesium carbonate. Oh, not magnesium. There we go. Good. Mg OH in parentheses 2. What is OH? Hydroxide. It's one of our polyatomics. Got it? So we would call this magnesium dihydroxide, right? No. When do we use the di, the tri, the tetra, when do we use that? Covalent naming only. This is a common mistake, okay? We only use the di, tri, tetra, yada, yada, yada with covalent naming. These are ionic, okay? So we would call this magnesium hydroxide. Okay. Let me pause and ask you guys a quick question. Why? Why do I not have to say magnesium dihydroxide, or magnesium 2 hydroxide, or magnesium bis hydroxide? Why do I not have to specify how much of my OHs I have? Yeah.
Is it because it's invariant?
What do you mean?
Because it'll always be the same, it doesn't change, like
What's always going to be the same?
the number of OHs.
Not the number of OHs.
Charge.
The charge on magnesium. Everybody with me on this? Do you get why it's important to recognize that something is variant versus invariant? Magnesium will always have a +2 charge. Hydroxide will always have a -1. Is there ever going to be a case where we just have one hydroxide with one magnesium? Not just sitting around, right? In the middle of a reaction in an intermediate, we'll talk about that later, right? We might end up seeing that, but that's not something we name. Got it? The whole idea with something being invariant, it's always going to be the same. So it's worked into the assumption, it's worked into the name. Chemists are lazy, I told you guys this, right? It takes more calories to write magnesium dihydroxide. Just like, yeah, just know that it has a 2+ charge. You guys with me what I'm saying with that, right? That's important. So the reason why we call things invariant, that means they never vary. Oh, I gotta write that down, that's really long. You guys get what I mean with this? That's why we name things the way they do. Always +2, we know we have to balance it out. Hydroxide always 1-, we need 2 of them. Sound fair? I'm gonna ask you guys the same question when we get to, I think the next slide has a bunch of variant examples. And there we have to name things a little bit differently. I'm gonna ask why that is, okay? Sound good? All right. What do we got? KCr2O7, what's that one? Potassium dichromate. Wait a minute, Dr. H. You just told me not to use the di, the tri, the tetra, and all that blah, 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 blah. You lying, blah, blah, okay? Is dichromate telling me how much of something, or is that the name of what the polyatomic ion is? The answer in this case is both, actually. There's chromate and there's dichromate, okay? So this is just part of the name, not indicating necessarily how many there are. So this one's a little bit tricky with that, okay? So dichromate is Cr2O7 with what charge?
Negative.
How would you know that unless you've memorized? Let's say you're on the exam and you forgot it. If I give you this, how would you know that Cr2O7 has a 2- charge? There's 2 potassiums. Potassium always has +1 charge. You with me on this? Everybody following along, right? Cr2O7, 2-, dichromate ion. Okay? Nice purple powder up at the top there makes a beautiful, orange color powder makes a beautiful purple color in solution there, right? You guys will probably use that a little bit when you get through one of the labs. Fair? Chemistry is chemistry. Chemistry has a logic. The logic right now to pay attention to is everything has to balance out. If we forget on an exam what the charge of something is, take a look at one of the other problems and see if you can work back what the charge might be, okay? 1 minus and 2 minus tend to be the most common charges for your polyatomics. We have one example of a 3 minus, okay? Excuse me, 2 examples of a 3 minus, and we have 1 example of a 1 plus. So if you need to guess at something, guess either 1 minus or 2 minus. But you know what's better than guessing? No, right? Okay? So, anyway, at the bottom, what do we got? Aluminum oxide. Dialuminum trioxide? Aluminum 3 oxide? No, that's aluminum oxide. Invariant, always gonna have the same charge, everything has to balance. Good? All right. More. All right, have at it. What do we got? Here's where things get a little bit tricky. Go back to your notes. Take a peek at how we deal with variant metals. Variant metals. What tool do we need to bring in to answer variant or to name variant metals? We name them using our Roman numerals, right? The Roman numerals indicate the charge on the metal, not how many things it's bound to directly, but the charge on the metal. Okay? So if you have something that's variant, you need to know what is invariant or constant. These are your oxygen and things like that. Most of it, right? Now we just need to figure out what goes in the document, right? So take a look at what it's bound to and what charge that would have, and then that would have to balance that. Perfect. But be careful, it's not just how many there are there, it's what charge that has to, right? No, that's only when it's covalent you use the ion triangle, right? So remember, this is, remember I told you I was about to ask you a question on the next slide? This tells me how many of that we have. Not directly, but it tells me what the charge is, and then that has to be balanced out by how many of those. Right, that's the idea here, right? So we're balancing charges, not directly with the atoms, although one makes the other, right? Okay. Yeah. So that's where you look at the periodic table, right? We would consider this to be invariant part of it, so we look at the periodic table and say what likely charge would it have based off of its location. Okay? The least number of steps to get to the closest noble gas, that thing. All right, check the troublemakers in the front line, right? Well, you guys didn't deny it, right? So those are tricky. Those three there in the middle are kind of tricky. So we have to specify the charge, right? So we have to use the lower ones. All right. So I'm going to run through the same thing. And you guys have probably heard me say it a million times now. If I say something a million times in class, that's a very subtle clue to you guys. That you guys should probably be thinking about this too, right? Very subtle. I try and hide it, you know. You have to develop a path to name things, right? Different rules at different parts of the path. Ionic, covalent, variant, invariant, okay? So we're under the ionic variant path. How do I know that it's ionic? Metal and a non-metal. How do we figure out metals versus non-metals? Periodic table. How do I figure out whether it's variant or invariant? Transition metal. We're looking at the middle block there on the periodic table. You guys with me on this? You have to run that through, otherwise you're going to skip a step or do this, blah, 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 right? And then you get it wrong. I make a rule with my organic class. I'll make it the same with you, okay? I'll allow you to skip steps if you guys get your PhD. Sound fair? So if you guys want to work from now until Monday and, you know, get your PhD in the meantime, then you guys can come in and skip steps. Sound good? That seems reasonable, right? We can do It's amazing what you can do with Photoshop and a lot of effort, right? You can make your own PhD art. Okay? The point I'm trying to say is don't skip steps. I don't want you guys to miss points, okay? You skip steps, you miss points. That's all I'm saying. Good? Okay, variant. When I'm dealing with variant, so follow along for a second. When I'm dealing with a variant metal, do I change how I name the metal itself? No, I just use the name of the metal. With me? All I do is add the charge on the metal as part of the name. Got it? Using Roman numerals in parentheses. If I have something that's variant, I have to have something that is unchanging with it, something that is invariant. The anion. Got it? Chlorines, oxygens, carbons, those are our invariant part of this. Does that make sense? What charge will chlorine always have? How do you know that it's always going to be 1 minus? Is that something you memorize? Well, you might memorize as you go through these practice problems because you see it over and over and over, right? But where do we get that 1 minus charge from? We look at the, and we count, we take the least amount of steps to get to the noble gas. That's how I'm getting those charges. Everybody still with me on that? This is important, okay? So each chlorine, I'm just going to write it bigger over here, okay? So each chlorine has a -1 charge. I have 2 of them. So overall I have a 2 minus charge. Everybody with me? I have 2 independent chlorines. Cl2 is not a polyatomic. I have 2 chlorines. How do we know it's not a polyatomic? Is it on your list? No. If it's not on the list, guess what you are? Monoatomic. With me? So I have 2 independent chlorines that are there. Each one has a -1 charge, a total of -2. Therefore, the iron has to have what charge? +2. Good. I'm looking at the anions, the individual charges, and what the total is. And then the cation has to balance that out. So I would call this iron, in parentheses, 2 chloride. Because the 2 tells me how many chlorines are attached to it. Is that how it works? No. What does the 2 tell me? The charge on the metal. And from there, I infer how many anions I have based off of what I know the charges are going to be. Everybody with me on this? That's important. It doesn't tell me that I have 2 chlorines. It tells me I have 2 chlorines because it has to balance that +2 charge. Okay? Iron 3 chloride. Okay. Good. Let me change colors and kind of drop down here for this one. Copper, transition metal in the middle of the periodic table, variant. I look for my anion. Oxygen. Oxygen is pretty much always going to have a 2 minus charge. How many of them are there? Just 1. Got it? That means I have to balance out my 2 minus charge. I have 2 coppers. What charge does each copper have then? 1 plus. All right, so I have 2 of a 1 plus metal then to add everything up to be equal to 0. Got it? So what would we call this? Copper 1 oxide. What would the next one be called? Copper 2 oxide. Give you guys a second. I'm gonna erase and make some space for me here. Well, I think maybe I can cram it all in so I don't have to erase. Let's do red, right? Fe2O3. 3 oxygens minus 2 each. I have 2 irons at what? +3, right? To be equal to 0. Everybody with me? So we would call this what? Iron 3 oxide, also more commonly known as? Yo, hit me up with some of that iron 3 oxide. Yeah, buddy, I got you.
Is it rust?
It's rust, right? So if you guys ever seen some iron rusting, that's all it is, iron 3 oxide. Okay? Impress your friends and neighbors. Iron 3 oxide. Okay? At the bottom, weird looking one. Tungsten 4. Carbide. Good? These are the tricky ones. These are the ones that you guys, if you're not listening to me and you don't practice, this is what you're gonna mess up. So don't mess it up, go practice it. There's tons of examples online, there's tons of examples in your book, there's tons in the notes. Please, 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 please work through it. Yeah, what's up?
Why is just like copper and then oxygen? What was that name?
So that's copper 2 oxide.
Why is it two? Sorry.
No, that's fair, right? So when you have a variant metal, you look at the anion that it's bound to. Oxygen always has a -2 charge, and you have one metal, so it has to bear the +2 charge to balance it out. Good, good, good. You guys feel a little bit more comfortable with these now? Right? You have to practice outside of here, you know why? It's nice and easy right now. There's no pressure, no grades. Dr. H is gonna help you along, right? He'll always give you the right answer. Life is nice. As soon as you step out of here, what happens? I'm hungry, I need to go talk to my friend, I need to go do this, I gotta write a paper, I gotta blah, blah, right? Life comes back in. And by the time you sit back down, you're forgetting how to name the different paths along the way. So you gotta get that practiced. And it's the reason why you guys can tie your shoes without thinking about it. You guys have been doing it so long every day, right? Unless you have Velcro. And you don't have to think about it, right? You guys get the point I'm making? You have to do this every day. Going to the gym, right? Practicing your sport, whatever you do. A little bit each day. I'm not saying an hour. Start with 15 minutes. Sit down, name 3 problems. If you get them all, go buy a Snickers, right? Celebrate life. Right? But you do have to do this every day. Okay? There is no magic. I promise I'm teaching you all the secrets, all the tricks, all the shortcuts that I know. But at the end of the day, you can't simplify this. You gotta be careful because there's some videos online like, here's a shortcut that makes everything work. And then you miss something. Okay? Because not everybody online knows what they're talking about. There's, I guess as we know it these days, there's fake news, huh? All right. All right. So a couple of just thoughts and comments and this and that and random things here, okay? So when are Roman numerals used? Main block metals form ion of one type, that's invariant. Main block, we're talking about groups 1, 2, right? 3, 4, 5, 6, 7. Any of the metals that are along the way in there. Okay, not all of them are metals, but I think you guys get the point, okay? There are some exceptions. Lead and tin. Remember I told you there's some exceptions along the way. If you take a look, so grab your periodic table, find lead, find tin. So tabbing over here, right? Here's lead, here's tin, right? Erase this stuff. Blah, 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 blah. Are they in the transition metal block?
No.
No. So we would think that they are invariant. These are one of the exceptions. But notice the relationship between lead and tin. They're in the same family, they're at the bottom. Things get weird when you get near the bottom of the periodic table. Right? Things get weird when you're the bottom of your family. Like me, I'm the youngest son. I'm a weirdo, okay? So, any other youngest siblings in here? We're all weirdos, right? Can we admit that? Yeah, all right. You guys get what I mean with this? They're in the same family, they're at the bottom, right? Those are going to be variant metals. All that means for you is that we have to name them using the Roman numerals. We have to name them using the variant system. That's all it is. Sound good? No different rules, just, hey, this is an exception, all right? Oops, wrong slides. We go to the other end, okay? Transition metals, the stuff in the middle, those are variant. We name them with the Roman numerals. Exceptions, silver and zinc, okay? Silver is always going to be 1+, although that's not necessarily true anymore. You know, science changes, things change. So what I should technically say is that for the purposes of this class, silver will never be anything aside from +1. Okay? Zinc will always be 2+. We will actually learn why that is in a couple chapters. Okay? Sound fair? So there's a couple random smatterings of exceptions in there. I think the book might talk about a couple more. I think it's this version of the textbook. Actually, you know what? I should have checked that, so I apologize about that. I'll look through it, but these are for the, if there's any additions, I'll send you, we'll talk about it next class. But for the moment, let's just stick with these unless there's an update, let's say it that way. Good? So tin, lead are variant, zinc, and silver are invariant. Doesn't change the rules, just how we deal with those 4 specific elements. Good? So I'm just summarizing stuff here for you guys, right? So this is all already in your notes, but if you guys are just looking along on the slides there, I'm just kind of putting everything together, right? Some generalizations. We have a metallic element. We just have a metal plus a non-metal. These are ionic. Non-metals are covalent. Metalloids, there's no easy way to tell if it's ionic or molecular. So what is this translating to you guys right now? I made you guys a promise, right? And the promise was for Jolly Ranchers. Well, I did, but what else did I promise you? I'm never going to try and trick you guys, okay? If I give you something, it's got to be obvious, or it's got to be something we specifically talked about in class where you guys can solve the problem. I'm never going to throw something at you and be like, ha ha ha, if they had their PhDs, then they could figure this out, okay? Anybody in here with a PhD yet? Good. We're all on the same level then, right? I didn't raise my hand though, uh-oh. Okay? Just found some guy in the street, come in and teach chemistry. You guys with me though? I'm not going to try and trick you guys. If I give you something, it's going to follow one of the rules that we have there. That's all I'm saying. I'm not going to throw some metalloid at you and be like, can you figure out what it is, right? I'm going to give you something obvious with it. I can give you a metalloid with a polyatomic ion, right? If the polyatomic ion's negative, guess how your metalloid's going to be acting? Like a cation. You guys with me on that? And then you figure out the rules from there. Sound good? So if you're ever stuck on something that you don't know, look for something you know. That's how life works, right? All right. Okay, now I give you no hints. You're on your own. The world is cold and cruel. It's not that bad, it's just naming. invariant, and it's invariant. Yep. That's okay. Remember, what's your path that we follow? Covalent, just like covalent or something. How do you know something's ionic covalent? I'm looking for what specific ones. Sulfate. Non-metal, metal or non-metal, non-metal. So how does that, are they, which one of those is a metal? These are your non-metals. Your metals are non-metal. So non-metal down to non-metal, so this is covalent. And then goes here, it's covalent. So no parentheses, no, Roman numerals. All right. So we're not gonna have time to go through all of these today, but let's give us a good start here. Be careful. I've put this on exams before and people come in and say, SO3, our good old buddy sulfite, one of our polyatomic ions. Is this a polyatomic ion? How do you know? There's no charge. Got it? We don't have a charge, it's not one of the polyatomics. It's just a good old regular covalent compound, right? So in black, that's a covalent compound. So you have to go through your covalent naming. With me? SF6. Sulfur, fluorine, non-metal, non-metal. Covalent compound, right? So your two in black there, make sure you name them with the covalent methods. Copper sulfate in purple. Is copper variant or invariant? Ionic or covalent? Copper's a metal. Sulfate is a non-metal. So it's ionic. Copper is variant, right? We have two variant ionic compounds. And we have, let's do green, invariant, and invariant. Okay? So black are your covalent, purple are your variant ionic, and green are your invariant ionic. And we'll pick up the names next time. Sound good? All right. So to get a little bit of practice in, you guys have a little bit extra time from class today there. We'll come back, we'll pick this up, and we'll probably wrap up chapter 2 next time.